Part 4, Direct Comparison Test. Before you write anything, please just take a moment and watch the following. Alright, I'm going to draw an axis, y-axis, I'm going to draw an x-axis. Then I'm going to draw a function g of x. Now g of x is a positive function, and I'm going to draw g of x from a out to infinity. And so this g of x function starts here and has asymptotic behavior down here as follows. Now suppose, let's label this yellow as g of x. Now suppose we knew that the integral from a to infinity of g of x converges, as we've described at earlier parts in this particular lesson. Suppose that is known, it converges. Now I'm going to pick a different function. I'll draw this function in red, and suppose this is also a positive function, but this positive function is always less than, or at least less than or equal to, g of x, and that can sneak in here. Can you guess what we would say of the integral from a to infinity of this red function f of x? Let's label it f of x. You could probably guess then that if we know that the function g of x converges from a to infinity, then if f of x is less than or equal to it, then we would say that it also converges. And that's the logic behind the direct comparison test. Okay, so let's take a look at another scenario. This time I'm going to draw a function. Let's call it still g of x. Okay, this has asymptotic behavior, comes down, it's going to approach the asymptote. And this is g of x. But suppose it is known that the integral from a to infinity of g of x dx, let's suppose it is known that diverges. Okay, it diverges. And then I'm going to pick yet another function, perhaps a greenish color, green on green, smart idea, Mr. Bermel. I'm going to pick an f of x, but this one goes from a to infinity, and this one is always bigger than g of x, like this. Asymptotic nonetheless, positive yes, but it's always bigger. Well, it's clear then if the integral of g of x diverges, then it's clear here that the integral from a to infinity of the green function f of x also diverges, f of x. So these would be two conclusive cases of the direct comparison test. I'm going to do a third one here. In this third scenario, suppose it is known that the integral from a to infinity of g of x dx, let's say that is known to diverge. And then let's pick another one. Let's, I guess this cream color. And this f of x is always less than or equal to it. And I can sneak that in here. So then what conclusion can be made of the integral from a to infinity of the cream f of x? This is our f of x. What conclusion could be made of that? No conclusion. No conclusion. No conclusion. Maybe it converges. Maybe it also diverges. We cannot tell from the information that is given. So in the direct comparison test, there are scenarios that lead to inconclusive results. And now it is time to use your notes packet to write the direct comparison test. If you write this in two columns, one to the left and one to the right, two different scenarios. So I'm going to say if. Okay, here are the ifs. Part 1 if. f of x and g of x are positive and continuous. Now, the way I'm writing, I'm not going to be able to fit my other if over here, but if you write small enough, you can fit them both on the same page. So, f of x and g of x are positive and continuous. Let me add to that on some interval a to infinity. Cross that out. The second if, so if that is true and also the integral from a to infinity of g of x dx converges. Now I may have said that g of x converges. I should have always said the integral of g of x converges. It would be wrong to say g of x converges. So 1, 2, and then finally 3. F of x is less than or equal to g of x for all x on the interval a to infinity. The upside down a means for all. Then, so here's my then statement. If all three of these are satisfied, 1, 2, 3, then the conclusion can be made. Can you tell me what conclusion can be made? The integral from a to infinity of f of x dx converges also. All right, let's take a look at the other conclusive finish. Okay, the second version starts off similar. If 1, f of x and g of x are positive and continuous on the interval a to infinity, that's the same. And 2, the integral from a to infinity of g of x diverges. And 3, what am I going to say here? Hopefully you know that f of x is greater than or equal to g of x for all x on a to infinity. Then, what's the conclusion? The conclusion is that the integral from a to infinity of f of x dx diverges also. That is conclusive. It conclusively diverges. The other scenarios are inconclusive. Example A, we want to prove whether or not this particular integral converges or diverges using the direct comparison test. So the first thing we're going to do is state that f of x is the function that's inside the integral. The function is the integrand. We're going to let that be the case. Next, we're going to define a g of x. Now see, we want to be able to pick a g of x that the integral we know converges or an integral we know diverges. So the skill in the proof is simply coming up with g of x. It's not a terribly hard skill, but it is the skill. After that, it's more memorizing the form of the proof. So if I come over here in the margin and I look at this f of x, but I delete the insignificant minus 0.01, then I'm looking at 1 over the square root of x squared, which then is making me think of 1 over x. Ultimately, that's the strategy for choosing the g of x. So I'm going to pick 1 over x. And the minute I pick my g of x, I should have a hint or at least a gut feeling whether or not my function is going to converge or diverge. Do you have this gut? Let's see as we go through. So I'm asking you to be very formal in the proof. So step 1, we're going to say that f of x and g of x are positive and continuous on the interval in question here would be 1 to infinity. All right, that's how we start them all. 2, we're going to say that the integral from 1 to infinity of g of x dx. See, I'm going to write this generic. I'm asking you to write this particular statement, the generic form, before I define the g of x. It helps to retain this. So this is the integral from 1 to infinity. Don't skip this. 1 to infinity of 1 over x dx. Now, what say you of this? This integral from 1 to infinity of 1 over x dx, we're supposed to know whether this converges or diverges. What do you think it does? Hopefully, based on the other parts of this lesson, you would say that this diverges. And then we need a reason by p integral. Remember, we defined that to be p integral with p equals 1. So this is a divergent integral. And then in step 3, the goal is to show that our f of x is bigger than the g of x. If we can do that, we'll show that the integral of f diverges also. So now my f of x, which equals 1 over the square root of x squared minus 0.01, is going to be certainly bigger than 1 over the square root of x squared. See, when the denominator, and when we're taking away from the denominator, it's making the fraction bigger. And then this is equal to 1 over x, which equals g of x. So we successfully showed that f of x is always bigger than g of x, and that's for all x on 1 to infinity. And therefore, let me just scroll down slightly, and therefore the integral from 1 to infinity of f of x dx, notice I wrote that generically, I'm going to ask you to do the same, which equals the integral from 1 to infinity of 1 over the square root of x squared minus 0.01, converges also by the direct comparison test. Final example, B, we're going to prove whether or not this converges or diverges using the direct comparison test. So we'll start off, f of x, sine squared x over x squared. G of x, the skill, hopefully you see this as 1 over x squared. Okay, let's write this out. First part is standard. F and g are positive and continuous on 1 to infinity. Part 2, the integral from 1 to infinity of g of x equals the integral from 1 to infinity of 1 over x squared dx. And we should know that this converges by p integral. P series is what we'll do later when dealing with series. P integral with p equals 2, which is bigger than 1. And step 3, then our goal is to show that f is always smaller than g. So f of x is the sine squared x over x squared, which is certainly less than or equal to 1 over x squared, because the sine is between -1 and 1. The sine squared is always less than or equal to 1, which is equal to g of x for all x on 1 to infinity. It may be true other places, but we want to specify the interval. And finally, therefore, we have another conclusive result. So the integral from 1 to infinity of f of x dx equals the integral from 1 to infinity sine squared x over x squared dx converges also by the direct comparison test. And I'm putting another smiley face. When we start doing a lot of tests to prove convergence or divergence, it's not converge is good, diverge is bad. It becomes conclusive is good, inconclusive is bad. And on that note, this concludes lesson 2.